In this video, I'm going to talk about molecular orbitals for larger molecules. And so larger means essentially 3 or more atoms. And so in the last couple of videos, we were looking at diatomic molecules, which are just 2 atoms. But in this video, I'll be looking at 3 atom systems. And in particular, I'll be looking at systems that are essentially like this. So a central atom and then 2 flanking atoms that are the same. And so for this, we need to actually find what are called the group orbitals of the flanking atoms. And essentially what we're doing there is we take the atomic orbitals and we sort of arrange it the way that it would look in the molecule. So for instance, if we wanted to look at the p orbitals of our b atoms here, we would do something like this. We often put a dot here to tell us that there is an atom between them, and then like this. And of course, we want to think about the sign of them. So we would do this for the sign. And then we would think about what happens when we do symmetry operations on this here. And so that would be sort of rotating around this point here or reflecting around that point right there and sort of come up with the point group for that. All right, and so then we would want to look for the atomic orbitals of A and C, which the symmetries of those, which ones would be compatible with these symmetries of our group orbitals here. And so then we would, once we find the compatible symmetries, we would then look to the energies to see which are the actual ones that will bond together. So we'll first examine a common model molecule, which is this FHF-. And this is used as an introduction because the hydrogen doesn't have these p orbitals, and so it doesn't add this sort of extra layer of looking for pi bonds. We will actually get to that in the next example in this video, which will be carbon dioxide, which has a carbon for the A atom and then oxygens for the B atoms. But for this first one, we'll be looking at hydrogen for the A atom and then fluorines for the B atoms. So the first step is to find the group to which our molecule belongs to. So this is a D infinity H point group, but that's difficult to work with. So I actually have the character table for that right here. We can see that this is it's a bit complicated. We have all these sort of, infinite continuations going on here. We have all these sort of cosines in here, and then you're probably looking at these term symbols here, and I haven't talked about those yet. I'll talk about those in a future video, but like I said, this just makes it confusing. But if we at first ignore the signs on the p orbitals, so whether it's a positive or negative, we can call it D2H. And so we can see here if we wanted to sort of rotate this, that this red lobe here ends up at the next red lobe, it would have to be a 180 degree or C2 rotation. And we can see how we would have the different reflections and so on going there. And so we can actually call it a D2H point group, which has the C2 rotations here. We have an inversion, which you can see we would have up here, and we have these different reflections here in the planes. And so we can call this a D2H point group here. And so we then find the representations for the combinations of the orbitals on the outer atoms, which are the 2s and 2p orbitals for the fluorine atoms, and that will give us these group orbitals. And so we have the z sort of pointing to the right. We have X pointing upward here, and we have the Y sort of pointing out of the screen. And so we look at these and we think about what the symmetry operations do to it, and these two px orbitals are B3U, or if we have it sort of alternating and the sign is B2G, and so that's the B3U up here and the B2G. And so we could go through and look at, if we do sort of a rotation around the Z axis, that this B3U would end up with the signs sort of alternating, because the Z-axis, remember, is this way. So we're rotating around this way. So these dark blue, or these blue ones will end up where the white ones are, and the white ones where the blue ones are, and so on and so forth. So you can go through these for all of these different symmetry operations. But for here, I just kind of already have the actual irreducible representation listed for each of these. And so we see that we have the B3U, the B2G, the B2U, the B3G, the AG, the B1U, the AG, and the B1U here. So the Ag1s orbital of hydrogen. So the hydrogen only has the 1s orbital, and so we know that's going to be the Ag symmetry. And so we can just already kind of assume that. And that's going to have the correct symmetry to interact with the group orbitals 1 and 3. And you see I have these boxed here because that's what I'll be kind of referring to these as. So 1 and 3 are these Ag symmetry ones. And so the Ag of the 1s hydrogen has the correct symmetry to actually interact with these group orbitals 1 and 3, which are also the Ag symmetry. However, the energy difference between the hydrogen 1s and the fluorine 2s, which the group 1 orbitals have this minus 40.2 electron volt, whereas the group 3 has this minus 18.7 electron volt. And so if we look at these energy differences, so the hydrogen has the minus 13.6 electron volt binding energy. The group 1 has the minus 40.2, so that's an energy difference of almost 30 electron volts. Whereas the group 3, which are the 2pz orbitals on the fluorine, has a difference with the hydrogen of only about 5.1 electron volts. And so it's therefore the fluorine group 3 that will bond with the hydrogen 1s orbitals. And so we can look at the energy diagram for that. So I have the fluorine groups down here, and often just by convention those are put on the right side of the diagram here. The group orbitals are put on the right side, and then the sort of atomic orbital is put on the left side here. And so we see all these group orbitals here, and when these come together with this 1s, we end up generating these molecular orbitals. And so in molecular orbitals, since we use capital letters for the symmetries of the group and atomic orbitals, we use lowercase letters for the symmetries of the molecular orbitals. And so we see that we have the Ag here, and then the Ag antibonding up here. So that's the Ag coming from the atomic orbitals there, and the Ag coming from these group orbitals right here. Then all these B1U, B2U, B3U, the B3G, the B2G, and so on end up in these non-bonding orbitals right here. So we see this one has a little bit of anti-bonding character, and that makes sense because this FHF minus is going to be very unfavorable since it requires that the H is making sort of two bonds here, which is very unfavorable. And so we do have this bit of anti-bonding character here, but the sort of energy difference is, we can see it's not great enough to sort of go even above the hydrogen 1s atomic orbital here, and so it's kind of a non-bonding orbital. Then we see here we have the 2s orbitals for our two fluorine atoms, and those are sort of very different in energy from the hydrogen 1s. In fact, we set up here, it was about a 30 electron volt difference, and so these both are non-bonding orbitals right here. So yeah, 5 of the 6 p orbitals from the fluorine atoms do not interact with the hydrogen atom and are therefore non-bonding. That is these ones up here. Though I said the B1U has a slight anti-bonding character. So the 2pz orbitals with the Ag symmetry form the sigma bond with the 1s orbital of the hydrogen. It also generates that sigma star orbital that goes unfilled. That's this one up here. And the 2 electrons in the sigma bond are delocalized over all 3 atoms. So we can kind of think about that looking like this. So we have the bonding, and so these electrons are sort of shared through all of the atoms here, which are kind of these little dots that I have here. And then we have the same thing for the anti-bonding here. All right, so then if we look at the CO₂, so we're kind of moving on from this FHF minus system here. We're now going to look at CO₂, which does have p orbitals in our carbon, so in our central atom. So the carbon sort of Lewis structure is the C, then we have the double bond O's going on here, and then the lone pairs on our oxygens. And so we are looking for the molecular orbital diagram for this. So we first established that CO₂, again, it's a D infinity H, but we can simplify it like above to the D2H point group. And so we actually end up with the same group orbitals for the oxygens as we had for the fluorines. And so that's this is all exactly the same as above, but we now need the symmetry of the atomic orbitals of the central carbon. And so this, now we have the 2s, but we also have these 2pz, 2px, and 2py. So these will have the following symmetries. So the 2s has the Ag, the 2px has the B3u, the 2pz has the B1u, and the 2py has the B2u. And so we want to look at which of these for the central carbon match up with these group orbital symmetries from the 2 flanking oxygens. We see that the carbon 2s is the correct symmetry to bond with the oxygen group orbitals 1 and 3, since those are Ag and this is Ag. We see that the carbon 2pz has the correct symmetry to bond with the oxygen group orbital 4. So the 2pz here is a 1b, there's a B1u, and this is a B1u up here, but also here. And I should actually have 2 and 4 right here. So I'll change that in the lecture notes, which as usual will be linked to in the description down below, but it has the correct symmetry to bond with the oxygen group orbitals 2 and 4. So I'll even put a 2 right here, so and 2. All right, and so we see that the carbon 2px is the correct symmetry to bond with oxygen group orbital 7, the 2py with group orbital 5, so 5 and 7. So we have the 5 and the 7 here. And so the 2py down here can bond with these 2py up here. So if we sort of sandwich this in between here at that dot right there, we see that the phases would all be correct. Blue would match up with the 2 blues for this, and the whites would match up for the 2 whites for that. Then the same for the 2px. If we sandwich that between these at this dot here, that those signs will all sort of come together. So those will actually be our pi bonds here that we will look at in a moment. All right, so these are the energies of the different orbitals here. So we'll first look at the Ag symmetry. So the oxygen group orbital 3, which has this minus 15.9, which is this one right here. So it's the oxygen group orbital 3, is only a 3.6 electron volts off from the carbon 2s. And so that's this right here, this minus 19.4, making them very likely to overlap. Meanwhile, the oxygen group orbital 1, which is going to be this one right here, is 12.9 electron volts off, making it much less likely to interact. The oxygen group orbital 2, so the oxygen group orbital 2, which is again this minus 32.4 electron volt, is 21.7 electron volts different from the carbon 2pz, and so that would be this one right here. And so these are unlikely to interact, and therefore the carbon 2s and oxygen group orbital 3 are most likely to form the sigma bond. So the group orbitals 1 and 2 will be non-bonding orbitals since there is not much overlap there. So the group orbitals 5 and 7, as I said, will form the pi bonds with the group or the carbon 2py and 2px respectively. The group orbitals 6 and 8 will be non-bonding orbitals. And so we can actually look at the energy diagram here. So we see this is getting a little bit complicated here, even just for a 3-atom molecule. So we have our sigma bond right here, which is the 2pz orbitals, or the group 3 up here, which is what we said is going to be forming the sigma bond. And so that's this group up here. So this group 3, so we have the same sign pointing inward and the opposite sign pointing out, which is what we have going on right here. And so we could go through each of these. So we have our 3b1u right here, which is this sigma bond going on right there. And so then we have our pi bonds going on right here, which we see has these p orbitals all aligned in the correct way, with the ones in the middle being the carbon pi bonds, or the carbon p orbitals, and so those are sandwiched between. Then we have these two, which are the non-bonding orbitals right here. We have the anti-bonding orbitals going on up here. And I think in the book I'm using, which is the Miessler and Tarr, it actually has these right here switched around from what is going on here, but the energies are going to be close enough that it's probably one of those things that, you know, it depends on what source you are finding, that those will be switched around. But I believe in my book this sigma star is actually higher than this pi star here, but you know, those are both unfilled, and so it kind of isn't going to affect anything here. And of course, then we have our 2s coming from the oxygens, which form these lone pairs, these non-bonding ones here. So we have the 2 lone pairs here, and we have these 2 lone pairs here, and that should accord with what we know from the Lewis structure, which has sort of 2 lone pairs. So we could think of, you know, 1 lone pair from here and 1 lone pair from above up here being on this oxygen, then 1 lone pair from here, and then this other lone pair up here being on this oxygen right here. And so we again are able to recapitulate our Lewis dot structure. But anyway, that was everything I wanted to talk about in this video. The next probably maybe 1 or 2 videos will be covering different you know, many atom or larger molecule molecular orbital diagrams here, sort of going through this process for even larger molecules. So things like you know, the ammonia molecule, which has 4 different atoms bound to it. So there's, you know, it makes things a little bit even more complicated. You have to do a little bit more, but the process is more or less the same. But anyway, I don't want to ramble on too long. I hope you found this video helpful, and I will see you in the next one.